In case you didn't hear that, this is Physics in the AM. Thank you for our welcome, Team Vector. Okay, we're taking up our problems from page 130, 22 through 26, friction and acceleration type problems. The first one, we got a head start. We'd already looked at the diagram, so I'm not explaining as much. What's the coefficient of kinetic friction between the block and the surface? You're assuming it's already left someone's hand or the push is done, and it's just sliding with only friction. In this diagram, you only show forces, but it should be understood that it's moving to the right. Now, I was going to explain how I mark a question like this. So, I typically give a mark for the diagram, correct. I give a mark that you've labeled, I'm going to change my color out. Anyway, that you've labeled x-axis, and you'd state Newton's second law explicit. Sum of forces equals mass times acceleration. Then a mark for subbing in. I'm tending on finding it's easier to be understood if you just say that I know that the force of friction is to the left, so I put the minus sign in there. You can opt not to and figure things out the other way. Anyway, so the subbing in and then the solve. This would be a 4-mark question. Okay? That's how I mark this. Is there any questions about this one? Conceptually, this one was a little easy. The first two were kind of 22 and 22. 23. Oh, wow, you can see already I have the marks down there. I must have went over this last year the same way. I marked the same year. This one had the push. As you're doing it, the force of friction working against it. X-axis, sum of the forces, plug it in, solve for mu equals decimal 1.5. Is there any questions about this? This is the time to do it. Now, I've actually explained, the next one is a lot tougher, 24, but I think I've explained most of the concepts of it. I'll wait for a minute on this. Like, I'm not sure if people understand. So, do you understand the diagram portion? Okay, so this is good. And then this is a gimme mark, basically. We're working in the x-axis, what we're trying to figure out. Then in the x-axis, and I coded it green, I'm saying that the friction is the subtracting, it's the left force. That part you understand? So then I say, well, the pushing force, push with a force of 65 newtons. That makes sense? Okay. Now, the force of friction, I'm subbing in the formula, mu Fm. Does that part make sense? So that's why I subtract mu K 401.8. I figured that out because it's the opposite of the weight. On the opposite side, the mass is 41 kilograms, and it was given that it accelerates ma. That part? Uh-huh.
I had this on one side, the story, and
Yep.
then I had the coefficient with the and then I times that by the 401.8, and then I divide both sides.
Okay. Did you have this right-hand side?
No, I don't know like how I ended up.
I don't know either.
It's like I have the right answer 12 times.
That would be, you must have done it somewhere but didn't write it down.
Okay.
Because I don't see any other way of getting that. Yeah. By accident. Like sometimes there's a coincidence. You guys at the back, what are you guys thinking? Or are you guys just writing it down and figuring it out? Okay, just wondering. I'm going to kind of go fast, you know. Time management. We'll see. Is this okay though? Okay, I'm moving on. 24. Now I talked this one through a little bit, right? Shuffleboard disc. Okay, I started out this way the other day, and I had you guys do it. I'm gonna flip back though, because I actually haven't fully worked out here. Oh my goodness. Now, if you recall, the other stuff I figured out the other day, right? And I left you with finding the acceleration. Is that correct? I think that's, yeah. So this rock is pushed, this shuffleboard coaster or whatever you call it, is pushed. So there's no force pushing it after it leaves your hand, a stick or whatever that game is. It's only the force of friction in the x-axis. You use that in the x-axis. I see. Sub in for the force of friction. Okay. I figured it out a different way last year. I usually go with whatever students tell me to do. I never see how I started. Okay, yeah. I'm flipping back and forth. Yeah, right. And we said, yeah, cancel out your, this is where we left off, right? Hopefully you solved from this point. I'm going to just go because the math is on the other page. Scratching out, and I have the numbers inserted. So this is where we left off with the first unit. Okay. So you put in G, 9.8, solve for acceleration. So this is a big problem. Now you go into the kinematics formulas, the non-force formulas to find the distance drop. So now we have an A value. We're going to plug that in. V1 and V2 were given in the problem. We'll just sub stuff in, and then the rest is algebra. So essentially, this is what I left you with, is the blue word here. I'm going to just read this. Is this what people were getting, 5.6? You can have positive 5.6. I don't mind. Okay. I think that's a rounding thing. That's not a, I'm not worried about that. Well, the way I worked it out the other day would have been positive. You know why? I think on this one, yeah, that's why. So that's why I'm not worried about that. That's always up to the diagram how you do that. Actually, this one should have been positive. Do I see now? I'm actually going to fix that. I don't know what we were thinking last. You don't know either. Okay. Anyway, that's the negative there, negative. I would have come up with signs, as long as you make sense of how your diagram works. Anyway, I'm not too worried about that. Yes? You can usually figure it out. You can leave it out. Like I say, most diagrams can be left, right, reversed. That's typically why the concepts are tough enough that I'm not going to get crazy on you about whether it's positive or negative at this point. Okay? That's what I'm saying. Because you could see 2 different years in a row, I had positive one year and negative last this year. Okay, yes. 0.31 is the mu value given here in concrete court. Okay. That's the mu value. Okay. Other questions about this one? I'll give it another second or two. These are conceptually difficult because they're sort of an A, B, C, D problem, like there's 4 things to solve. I'll wait for 10 more seconds and then zip over. Just double checking though. You have a bit more to copy or understand? Okay. Because everyone's important. Okay. 25. 25 is actually easy if you just read the actual given problem or the example problem. Consider the force pushing the box in example 4. How long would it take for the velocity to double to 2 meters per second? You read example 4, the velocity starting is 1 and goes to 2. Also from that problem, the example problem, you should have read that the acceleration is 2. That was the whole point of that sample problem, 2 meters per second squared. So when you read this, sure, there's a diagram you can have. This friction's working to the left the way I drew it. Pushing force is 98. But it really is not so much a force problem as it is just using these equations. So this was actually easier than the other, but you had to read through an example. Because you really didn't need it to solve this problem. Yes. Probably not for this problem because really you didn't need it to solve this. Okay. If it's a forces problem though, you typically need this. This is really just copied out from this diagram right here from the textbook. I just recopied it. Under half a second. People with me on that? Now that's just algebra. That I forget this one here. Let me read it carefully. Came in, is driving along on a rainy night at 23 meters per second. Sees a tree branch, the road slams on the brakes when the branch is 60 meters in front of him. The friction between the locked tires and the road is 41. Yes, so that's a mu value. Will the car stop before hitting the branch? So does it stop within 60 meters? Newton's law tells me it's a 2,400 kilogram car. So my weight force is negative 23,520. That's my normal force positive, right? I work those out. You really could use Newton's law to figure that out, but it's so simple. It's not accelerating up or down. So I just say just do the opposite, right? It's the x-axis that we really have to figure this out. So we say sum of forces. It's braking 100%. There's no engine working towards it. So it's 100% just the friction force. We solve that. We get an acceleration of negative 4 meters per second squared. 4.018. Okay? That makes sense with my diagram because it's stopping. So it's in the opposite direction to the motion. Is there any questions at this point? So I would give a mark for the diagram. We'll give a mark for x-axis, sum of forces, plugging that in there, and then mark for plugging in the numbers, finding acceleration. This doesn't solve the problem yet, though. You use that acceleration with the initial speed of v, 23. You know that it's braking, so v2 would be 0. You're going to find the distance and compare it to 60 meters. Question? It hits the branch. It would take 6 more meters to stop. I want you to have good enough stuff that you can understand it without a textbook in your notebook. You're going to have, like I say, I'll have an open book, kind of work these problems out with. And it'll be on your own, not a chit chat. I haven't decided because we still have to do the incline problem. I have to make it up. I just gave myself a sticky note to make this open book quiz. And I'll test you on all of the stuff, but I'm saving these hardest problems just strictly as open. Yep. Yeah. You thought these were tough. We're going to use sines and cosines again, vectors. This is why I didn't test you guys on vectors in the last unit, because I know you'll get more vector practice. Basically, it turns into trigonometry problems mixed with algebra. What it is. Okay, forces in motion in 2 dimensions. This is on an angle, as you can tell, a ramp. I'm going to get you guys to copy out the problem. We'll work through it together. I have the diagram for you. We'll see. Okay? Okay. 2 dimensions. Now, I put on here, and I'm going to just mention something here. Okay, we understand the triangle to be the ramp. I put on here that I have an XY axis. I'm not using an exactly horizontal x-axis, because it makes more sense and it's less math in this situation, easier to understand. If we put the x-axis at the surface of the ramp, okay? That's why I have that x right here, and then the y, 90 degrees, perpendicular, right? So, coming up with that diagram is important here. I'm going to explain it a little more before we start the problem. Here's my free body diagram. I've got my box there, and it's resting on the incline plane. Now, the box itself, gravity works straight down, so it doesn't, right? That's the 562 that's given. I'm going to just demonstrate here. Now, this is the 562 newtons, but we understand right now the way this book, right now, okay, right? It's same up, same down, the normal force. Once I start angling it, it could start sliding like this, right? I'm just trying to find that one spot. That's just this side. It's actually more friction. There you go. It broke the kinetic friction or static friction. Okay. Anyways, so you guys understand this diagram, what we're talking about. The weight force is always straight down. The normal force, though, on the other hand, is always perpendicular to the surface. So that's why my normal force is going like this. Yours should be on your diagram. Okay. The 30 degrees was given. And we know that the tendency of the box will be to slide down the ramp. So that's why I said my friction force is going up the ramp, the x-axis. Now, the first question that's kind of guiding you through this is, find the components of the weight parallel and perpendicular to the ramp. I didn't give the mass of the object. You could find it, but only find it if it's needed. It isn't in this case. Some problems you might have to work backwards and find the mass. So what I'm really thinking here is this weight force is my xy axis has an x component and a y component. It's not, you know, with my angled xy axis. So what I'm going to do here is I'll use this pen again. I'm going to just redraw this. I'm going to move it. Okay. Now that's my xy axis, blah, blah, blah. X, Y, and I'm only interested in the weight force. You guys know your codes, but is that a red for the FG?
Yeah.
Okay. That was a given thing, right? I'm just isolating that one because it gets too messy if I try it all on the same time. Parallel and perpendicular to the raft, so the X and the Y component. What I'm going to do right now is just draw in a right triangle here. So do you guys see what I did there? That's just a right triangle. And I know how math works. I think you guys do too. So this is 30 degrees, right? By similar triangles. What is this tiny little angle here? So essentially what I'm asking is if I draw this here, what is this angle right there that I've colored in? By similar triangles. Isn't that 30 degrees as well? No, you don't see that? Okay, we'll go through a little bit of a geometry thing. How about this? On the big triangle. This is 30 degrees, correct? This is 90 degrees, right? What is this angle here? They add up to 180, right? 30, 90, 60. Okay. I'm going to label in the 60 degrees right. 60 degrees. Then that other one, the one I was asking about, the tiny one on that, is 30 degrees as well. A similar triangle. A few ways. I like using the 60 degrees. I like measuring the angles to the x-axis. Then you can basically, without thinking, use the same sine and cosine steps for everything. Okay? So let's go back to red. Find the components of weight parallel and perpendicular to the rim. So I'm going to call this, I'm going to change my color. No, FGX. The force, the weight force in the y-axis, the weight force in the x-axis. Just to label my sides of my triangle. Now, the force of gravity in the x direction. Just follow where that is on the diagram. It's basically what's pulling it down the ramp. Solving that, is that involving the cosine or the sine of the angle? 60 degrees. So, 50-50 chance you're wrong.
No, I'm not.
It is the cosine. Now, where am I getting this? Okay, here's 60 degrees, right? The opposite is the y. The adjacent is the x. Okay. So it turns into, and I'm going to draw this out, and then I'm going to just skip it. I'm not going to actually use it because it gets to be repetitive. I'm going to do it in green because I'm going to erase it. If I was to say that the sine of 60 degrees, or the, no, we're using the cosine. Sorry, I had what you said in my head. The cosine of 60 degrees is adjacent, so f over the hypotenuse, which is 562. If I do this, and I isolate for FGX, it just turns into multiplying, right? Like what I'm saying is that I now multiply this side by 562, I'm squeezing it in, and this side by 562. Okay? These cancel, and there you go. Do you guys follow where this comes from? So what I'm going to just do, I said I'd erase this green stuff, because it turns into, it's repetitive. It's the same thing all over and over. I'm going to go with 562 newtons cosine 60 degrees. And as long as you always put your angles to the x-axis, you can just always say, well, the x-axis is the cosine. The y-axis, for the same reasoning, is 562 newtons, but this time the sine of 60 degrees. Okay? Now, the way I drew this triangle setup, would my x arrow be going to the left, negative, the x-axis, or positive? The way I have it drawn. That would be consistent. This time it does not. Is this negative or positive? Well, you look at the diagram here. This is what I'm talking about, right? That's to the left. So I'm going to make this a negative. I'm going to just insert that there. We know it's a negative. I would use my calculator. I have it worked out from before. Negative 281. You told me why that needs to go. Likewise, for the y-axis, it's going downward, so I'm going to call it negative. You got to make that decision. And that is when I calculated 487. Okay? Now, is there questions about the negatives? Okay? I think we've done it. We've got components of weight parallel and perpendicular to the ramp. Okay? And find the normal force. Now, the normal force is perpendicular to the surface of the ramp. The normal force is always equal and opposite to the gravity force if it's horizontal, but it isn't. Do you see that the normal force will be equal and opposite to the y component of the weight force, the gravity force? Because that's perpendicular to the ramp. So the work is already done, it's just recognizing. F n is equal to positive in this case. 487. Now C, find the force of friction. I got to read carefully here. Okay, I didn't fully explain this. Oh, box is resting on an inclined ramp at 30 degrees from the horizontal. What I didn't say is that this is just about, and I'll just explain exactly what this is. Watch this. Just as it's just starting to slide. So the static friction. So we're going to assume that this is just on the verge of moving. But I didn't state that explicitly. I'll use a different word than verge. Just about to slide. So we'll say that it's equal and opposite to the static friction. So we're going to say the x-axis, sum of the forces, mass times acceleration. It's still just about to slide. So we've got a force of friction on the left. Where I drew it, yeah. And it's equal and opposite to the x force of gravity. hang on. I didn't draw it that way, so I'm going to put it the other way around. Force of friction is positive. It's subtracting force, gravity. Saying that it's just on the edge of slide. But it's still zero. It's just about to move. That makes the math easy. So when I do this, the force of friction is equal and opposite to the absolute value of the gravitational force. I put in the minus sign already for the gravitational force because I'm saying it's not actually, it's just about to slide, so it's not accelerating. Yes? 0 times the mass, acceleration. And we're using the absolute value of the gravitational weight force because I already put in the negative sign right here. Okay. So what was that? I can slide up again. 281. Okay. In this case, force of friction, 281 newtons. I'm going to have the same problem with different objects and stuff like this right away. I'm going to get you started on it. It's the same problem. Use this as a guide. So, a coin is placed on the cover of a book, and I don't have a coin right now. Usually I do, whatever. Yes, I remember. So, essentially, this book is placed on the cover. When the cover makes an angle of 38 degrees, it just starts to slide. So we're going to assume that we're talking about that point where it just about starts to slide, acceleration is 0. So it's the same problem with the horizontal. What's the coefficient of static friction between the cover and the coin? This time you're going to have to find FF and then plug in mu Fn to find. Okay? So it's really the same problem with one extra step. And you can make this assumption. I'm going to just put the x, put this on here, xy. And then for the coin itself, use a box just to make a free body. It's essentially the same diagram again. And I didn't ask you to come up with the x and the y component of the weight force, but you're going to have to. And you guys, I just moved the xy axis over to the right just so you understand what it is. It's less messy diagram. Go with this. Use the other thing as a guide to solve that. I'm going to give you guys time to do it, okay? Let's just see what we can do here. Like I say, it's the same diagram as the other one. You got a weight force that's straight down. A normal force that's straight up. It's not drawn very well. We're going to undo it. Because it locks it all together. Yeah. My normal force, straight up. Okay. Phone call, but I'll pause. This is the normal force. If it's going to slide, it's going to slide down the lamps. The force of friction is against the probable motion. 38 degrees. coefficient of static friction between the cover and the core. Okay. It's essentially the same problem. I didn't tell you to break down the weight force, but you got the weight. Once again, FG is equal to, I didn't tell you everything, did I? So, yeah. Do I need it though? You don't always need every measurement. Well, kind of. This is why I'm going through. It's supposed to be a Y. That's a messy. Let's go back to this. We don't need it. We do know that FGX well, we've got to figure this out again. What is the angle that's right here? We go with the 90 minus 38, right? What is 90 minus 38? I don't remember. Oh gosh, 52. Yeah. 52. That's 52 degrees. Okay, now we can do it. It is the original FG value times the cos, 52 degrees. The Y component somehow slipped out on me. This is tricky because I don't have the numbers, but it's the same thing. Take the hypotenuse times the sine of the cos. You guys follow that? So this is abstract, is it? Doesn't have actual numbers like 322. We want to talk about static friction. So that's going to be the x-axis. And I'm going to flip back for a second here under 1 minute. I understand. That's the wrong one. I flipped back to. There we go. We use those values. Oh, there we go. Find the normal force. And that's just the opposite. It's just FG, but positive. And then it's the same process there, but we'll talk about it tomorrow. Okay?